Now exercise 23. It reads, a circular loop of wire with radius 0.0250 meters and resistance 0.390 ohm is in a region of spatially uniform magnetic field, as shown in the figure. The magnetic field is directed into the plane of the figure. At time equals 0, magnetic field equals 0. The magnetic field then begins increasing with an equation or with a rate of 0.380 Teslas per cubic second times time cubed. And so it gives us Tesla in the end, since time would be in seconds as well. What is the current in the loop, magnitude and direction, at the instant when magnetic field equals 1.33 Teslas? So I have that all written out here. We have the loop drawn with its radius of 0.025 meters, its resistance of 0.390 ohm, and its changing magnetic field of 0.380 times t cubed, B0, 0. So we're trying to find what the current would be when the magnetic field is 1.33 Teslas. And so we'll call that moment in time t1. So first we're going to find when that moment in time happens so we can plug it in after we have everything else figured out. And so b of t1 equals 1.33, which equals our original equation for b, 0.380 t1 cubed. And so we can solve for t1 from there by dividing 1.33 by 0.38 and then taking the cube root of it. And so our time in this moment, is 1.52 seconds. And so that's important to have. So we have t1 equals 1.52 seconds. And now we can't quite plug in yet because we're going to have to use calculus with that still as a variable before we get to the final point. But when we get to the end, we'll be able to plug it in and find our answer. And so to find the current, we need our EMF, our induced EMF, which is dB dt times area. And we would take the cosine between the area, the direction of the area, and the magnetic field, but they are parallel. So it's cosine of 0, which is 1. So we can ignore that factor. And the area is not changing, so that's why we don't have to consider it in the derivative of the flux. Rather, the EMF is the negative of dB dt times A. And so we must find the derivative of our magnetic field in terms of time, which conveniently we have the magnetic field in terms of time already, and so taking the derivative is really quite simple. It becomes 3 times 0.38 times t squared, which number there is 1.14 times t squared. And so we have it to our EMF equals our negative 1.14 times our t1 squared times our area, which we can find with that radius, which ends up yielding for us our EMF, which we can then divide by our resistance, which resistance is 0.390. So that gives us an answer of 13.2 milliamps. And it comes out as negative 13.2 milliamps, which tells us that it will be in the end counterclockwise. So that is our answer.